Justin here is my first student to graduate today. I'm a solo advisor. So like Cynthia, Justin helped me to build the lab and helped me to make progress during the pandemic. In the basement with Cynthia, they had the mini cheetah and did all these experiments that were amazing, and then we ended up publishing papers on them. So Justin has worked a lot in the lab and did a lot of field robotics and collecting real data, which that's pretty much most of the recent field robotics, except the mapping work we did. And it's been a journey and great to have Justin in the lab, and I feel very lucky. We published a lot of good papers, and I'm proud about those works. And the stage is yours.
Thank you, Mani, for the kind introduction, and thank you all for being here today. Today, I'm going to talk about computational symmetry and learning for generalizable robot perception. So, in the beginning of my PhD, we received this mini cheetah robot from Sanbei at MIT. At the time, mini cheetah was blind, so we built a sensor suite to put on top of mini cheetah. We hope that it can see the world and understand the world, and eventually, maybe it can autonomously navigate through the forest. But then we quickly realized that all the sensor measurements, we need to quantify them with respect to some coordinate systems. Those coordinate systems are useful, but they are fundamentally arbitrary, assigned by humans. And at the time, the perception systems often treat the same measurements in two different reference frames as completely different. Like the cat here, if we describe it in reference frame 1 and reference frame 2, the numbers will look completely different, but they should be the same. In the field of physics, physicists have encountered this problem before, and they figured out that the laws of physics should not change regardless of the reference frame of an observer. And this is actually the foundation of Einstein's special relativity. And this immunity to a possible change can be categorized using the term symmetry. So we want to do the same thing for robotic perception systems so that it models the intrinsic properties of the world. So by studying the symmetry of the system. By doing so, we hope to reduce human-induced error. In the machine learning framework, we want it to be more data efficient. And we want the algorithm to be able to generalize to different transformation automatically. So there are two terms I want to introduce. The first is invariance. Invariance means that the output of the function is unaffected by the transformation that we apply to the input. For example, if you look at the image on the right, the input image is rotated, but the learn feature remains stable. Another term is equivariance. Equivariance means that the transformation on the input affects the output in the same way. So that when the input image is rotated, the learn feature got rotated by the same amount. And there's a mathematical concept I want to introduce before I dive into details. That is Lie groups. A Lie group is a group that is also a differentiable manifold. I often imagine them as a smooth curve on an n-dimensional space. Each Lie group comes with a Lie algebra, which is the tangent space at identity. The Lie algebra is a vector space, and it locally captures the group structure. And I also imagine it like a tinfoil on a curve ball. We can wrap this tinfoil onto the ball, and there will be almost one-to-one correspondence between the two locally. So just to give you a sense of what they are, let's take rotation as an example. The rotation itself lives on the Lie group, and its angular velocity lives in the Lie algebra. And in this thesis, we are going to focus on matrix Lie group and matrix Lie algebra. So even though Lie group is a more abstract object, you can safely imagine them as matrices in this work. So the thesis consists of 4 main chapters. The first one, I'm going to introduce a symmetry-aware state estimation library that runs real-time on a variety of different robots. The second part, I'm going to talk about a learning-based full contact estimator for Lego robot state estimation. Then I'll talk about a neural network designed to take the algebra elements as the input data, and it's adjoint equivariant. Lastly, I'm going to talk about a perspective-equivariant neural network for image representation learning. So I'll start with the state estimation problem. In the state estimation problem, we're interested in estimating the robot's position, orientation, and velocity with respect to some fixed inertial frame. Specifically, we focus on using proprioceptive measurements. What that means is that we don't use vision sensor. And this is the reason. When the robot like mini cheetah, when they walk into a forest or something like that, their vision can be blocked, or when there's a sandstorm on an autonomous driving scene. But we still need to control the robot, and we need some sort of state estimate, even though the vision sensor fell. So we focus on proprioceptive measurement in this specific work. For proprioceptive state estimation, many people use Kalman filter. Kalman filter is a two-step process. We have a prediction step where you use the robot dynamics to predict where the state will be in the next step. Then when you receive a sensor measurement, you use the sensor measurement to correct the system. But the robot dynamics is oftentimes nonlinear, so we need to do linearization with respect to the current state estimate. However, if the current state estimation is incorrect, that would give us a wrong linearization. And if it's really wrong, that could lead the filter to diverge. Symmetry can help with this. If we define our state instead on a matrix D group, like the rotation or rigid transformation SC3, then we can track the invariant error instead of the state itself. And the invariant error is defined as like the inverse of the true state times the estimate state. If we define the error in this way, any new transformation L that is applied to the system will be canceled out in the middle. And this error would reflect the true error of the system. So Baru and Banabo, they based on this observation, they developed this invariant Kalman filter framework. They show that if the system dynamics is group affine, the error dynamics of the system, which we're tracking, can become a linear system in the Lie algebra. What's more is that the linearization then will become a constant. So they do not depend on the state estimate anymore. We'll always have a correct linearization. And they show that the invariant EKF can have a great consistency and convergence property. So based on these invariant EKF algorithms, we built a C++ library called Drift, which runs real-time on all these robots, including Lego robots, vehicles, wheel robots, and marine robots. In the Drift framework, we use the IMU to do the propagation instead of using the robot dynamics. So IMU gives us angular velocity and acceleration, and we use that to integrate for the next step. In the correction step, depends on what robot we're using, we have different modality. For Lego robots, we can use foot position to correct the system. For wheel robots or marine robots, we can obtain velocity and use it to correct the system. So now let's take a look at some results. This is one of the military full-size vehicle that we went collected data in Pittsburgh. The vehicle has a IMU and a shaft encoder on board, and that's the only two sensors that we're using to do state estimation. This is a result of it. The blue line is the result of drift. The green line is the result of a air state Kalman filter that does not use any symmetry properties. And you can see qualitatively and quantitatively, drift has a better performance compared to the non-symmetry preserving state estimation algorithms. In order to test the limit of drift, we drove these Husky robots on campus for about like an hour. And want to see that without using vision sensors, how far we can push this algorithm to go. And qualitatively, it's like this. For about 3 kilometers, there's only 100 meters of drift. This is great because this means that even though our vision sensor is blocked, we can still track the robot for an hour without the robot being lost. So I talked about wheel robots. Now let's take a look at Lego robots. Ross and Jesse, they've done fantastic work on Cassie using the invariant EKF algorithms.
With money.
And money, yes. and Cassie has spring on each leg, which can be used sort of as a contact detection method. But there are some robots like Mini Cheetah that does not have a contact sensor on the foot. without a contact sensor, without a contact event, there's no way for us to do foot position correction in the filter. So the question is, how do we accurately determine the contact event given the sensor that we have? So we build a one-dimensional convolutional neural network, which runs real-time on the robot. It takes MU measurements, which gives us linear acceleration, angular velocity, and the joint encoders from each leg as input, and estimate the full contact events, like which leg is in contact with the ground in real time. In order to train the robot, we collect a quadruped contact data set on a variety of different terrains. And we also lift the robot up to the air to give some negative examples to let them know that that is not contact, even though its foot is moving. This is a qualitative result of full contact estimation. You can see that when the robot is first in contact with the ground, its foot actually bounces up. But that is fatal for a state estimation because that's not a zero velocity assumption. But our state estimation, our contact estimator can reliably remove that from estimating as contact. And here are some quantitative results. We compare with the dynamic equation of motion, which will compute the ground reaction force of the legs. Then we set a threshold on the ground reaction force to use it as a contact. We also compare it with the gate cycle command, which we assume the command from the controller is perfectly executed. And you can see that on 3 different types of terrains, contact estimator that we propose has a better accuracy compared to the other 2 methods. So then with this contact estimator, we can put everything on the robot, the mini cheetah, and perform as the estimation. We drive the mini cheetah robot that's just next to the FRB across many different types of terrains, and it performs the estimation with a contact estimator and drift. So qualitatively, the trajectory aligns with the satellite image.
Did you try using torque also as a feature? Or?
Yeah, that's one of the ideas that we originally thought about. But mini cheetah robot, at the time, we cannot access the real torque from the robot. Yeah, so we eventually didn't use it. So just a brief summary of the first part. I talk about Drift, a robust real-time state estimation library that uses symmetry into the framework. I also talk about a learned contact estimator that can help us do the estimation on robots that does not have a contact sensor. The second part I'm going to talk about is a Lie algebraic neural network design. So previous chapter, I talked about how we can use model-based approach to do state estimation. And a question naturally arises to us is that, can we design a neural network that models the robot's dynamics, but also respect the symmetry of the system? So back to this example, rotation lives in a group, and then the angular velocity of it lives in the Lie algebra. We want to answer a question that, can we learn the dynamics of a free rotating system that is robust to a change of reference frame? So we developed these Lie neurons. This is in collaboration with Dr. Minghan Zhu. Lie neurons is a multi-layer perceptron neural network. It takes elements in the Lie algebra as the input, and it is equivariant to the adjoint action of the group. So the group acts on the Lie algebra element naturally by the adjoint action, which is a G inverse here, you see. We want a neural network F to commute with this adjoint action. So before looking into how we can design Lie neurons, we need to take a look at how other neural networks are designed. First is multi-layer perceptron, MLP. In MLP, each neuron is a scalar. And then when we have an input, let's say a point, XYZ, after passing the first layer, the XYZ geometric position got mixed up together. So there's no geometric information preserved in the system. It's all get mixed up. So MLP is not equivariant. Vector neurons, developed by Chongyue et al. From Stanford, they treat each neurons as vectors. And by preserving this XYZ geometric dimension, when the input is rotated, this rotation got automatically propagated through the whole network, and then the learn feature is also rotated. In linear neurons, we want to do more than rotation, and we treat each neurons as an element in the Lie algebra. So it's not just a R3 vector. And we want it to be equivariant to this adjoint action, so like the conjugation action you see here. So a very quick summary. Traditional MLP is not equivariant at all because the geometric information got mixed together. Vector neurons is equivariant to SO3. Lie neurons is equivariant to the adjoint action. And I want to point out that when we work with SO3, Lie neurons becomes vector neurons with additional modules that we propose. So Lie neurons is a superset of vector neurons. So let's take an overview of the module in Lie neurons. The first part is a linear layer. So we also have a linear mapping to map the input data to a different linear mapping data. We have two specially designed nonlinearity that allows us to have adjoint equivariant nonlinearity. We can also have downsampling of the data of the feature, so we can reduce the feature dimension. Then we can also get the invariant feature, where the feature will not change no matter how we transform the input. So now let's take a look at how we can design the two nonlinearities. Before talking about how we design the generalized ReLU, I need to talk about what a killing form is. Killing form is a bilinear form that takes two Lie algebra elements and then output a scalar. And the killing form is adjoint invariant. So when the input data is transformed by the adjoint action, the value of the killing form does not change. When the Lie algebra is compact, this killing form can be used to define the inner product. So now let's take a look at how we can use the killing form to design the generalized ReLU. For one-dimensional ReLU, which everybody uses in their neural network, the input x is a scalar, and then we use x as a switch. When x is smaller or equal to 0, we clip the value back to 0. When x is bigger than 0, we keep the value. So we use this yellow line here to decide if we want to clip it or keep it. 3D ReLU developed by Tzu-Yuan et al. In vector neurons, they generalized this idea to 3D. So now, instead of just using a fixed line to decide, they first learn the direction k. And perpendicular to this direction k, there is a yellow plane. Any vector input that is above this plane, we keep it. Any vector input that is below this plane, we project it back to the plane and only keep the part that is above the plane. So in their 3D ReLU, they use the inner product as a switch. In our Lie neurons, we decided to use the killing form to relax the positive definiteness of the inner product. So we use the killing form as a switch. And an interesting fact is that when we are working with a compact group like SO3, this generalized ReLU reduces to the 3D ReLU proposed by Tzu-Yuan et al. A second nonlinearity that we have is the Lie bracket nonlinearities. Lie bracket is an operation that takes two Lie algebra elements as input and then output another Lie algebra element. And when the Lie algebra is a matrix Lie algebra, which in our case we focus on, we can write the Lie bracket as this commutator, just xy minus x, yz, yx. And Lie bracket is adjoint equivariant. So when we apply adjoint transformation to the input, it got propagated out to the output. The Lie bracket itself captures the non-commutativity of two elements. What it means is that if x and y commute, the Lie bracket value will be 0. So it only captures the part that doesn't commute. Based on this observation, we design a Lie bracket nonlinearity. So it's something like this. We have our input x as elements in the Lie algebra. We first use some linear ways to map them to two different Lie algebra elements. Then this Lie bracket captures the small differences in the non-commutative part. And we add these small differences back to the original signal. So in a way, this deep bracket nonlinearity is learning the differences gradually and add it back to the original signal. So with that, with those two nonlinearities, we have our full system like this. We have linear layers, two nonlinearities. We have pooling layer using the Killing form, and we have invariant layer using the Killing form, because Killing form is an invariant function. So now let's take a look at one of the experiments that we have. We want to learn a free rotating rigid International Space Station, where we use a Euler equation of motion to generate some simulated data. We use the neural ODE framework to learn the dynamic of the system. The neural network learns the underlying vector field of the dynamics. So each time when we query the position of the to the neural network, it outputs the velocity at that position. And then outside of this neural network, there is an ODE solver that queries the neural network each time, get the velocity, and then integrate for one step, then query for another position, and then keep going on. So this is a result. The upper part is the qualitative result of the learned dynamics, and the bottom part is the quantitative result. You can see that linear neurons has a better performance compared to the MLP. And what's interesting is that if we do a change of reference frame, which is a rotation on the input data, the neurons' performance remain the same, but the MLP completely fails. We can also apply linear neurons to point cloud registration task. In the point cloud registration task, we have 2 point clouds, and we're trying to find a rotation that best align the 2 point clouds. And the 2 point clouds are not exactly the same. They are corrected by some noise. We compare our methods with vector neurons and KV-conv. And you can see that KV-conv performs worse than vector neurons and linear neurons. And linear neurons, because we have extra nonlinearities like deep bracket layers, we perform even better than vector neurons itself. So in summary, in this chapter, I talk about a symmetry preserving the algebraic network that we designed. I also showed that how it could improve performance in dynamics modeling and perception, like a point cloud registration. Next, I'm going to talk about a construction of perspective-equivariant representation learning framework. So this is an image of my cat that my wife drew. That's it. If we have a planar object in 3D, just like a painting like this, if we view it from different angles, we will see the image like the other three. And assuming we know that they are the same images, we just look at it from different angles. We can even gauge what angle that we are looking at. We can erase that result. But we want the robot to be able to do the same thing. And it turns out that if the object is planar, its projection onto 2 different image frames can be modeled exactly using this homography matrix. A homography matrix is a 3x3 matrix that is line-preserving transformations, which includes rotation, scaling, shear, perspective transformation, and so on. And it can be captured using the spatial linear group, SL3. So in this part, we want to design a neural network that is equivariant to these perspective changes. So previously, I talked about point clouds. The group action on the point clouds is simple to define because point clouds are just a collection of points, which are R3 vectors. And the action on the points are just the left transformation on the point. But the image are mostly modeled as functions, which is a mapping from pixel coordinate to RGB values. What does a group action on a function look like? Turns out that if the function is a scalar field, so it's mapping from Rn to R, then the group action will only be acting in the domain of the function. So what it means is that it transports the point to a new location for all the points in the function. If the function is a vector field, which is a mapping from Rn to Rm, then in addition to transporting the vector to a new location, we also need another rotation outside of the function so that to align it to the correct direction. Okay, now we can look at convolutional neural networks. In the literature, people have shown that convolutional neural network is one of the best way to do image processing. It's an inner product of the function f and the kernel k. Basically, each time we just shifted the kernel and then perform inner product of them. The standard 2D convolution are translational equivariant. What that means is that if the input cat, like this, is shifted to a different location, then the learn feature of the cat will automatically be shifted to a new location. We want to generalize this to beyond translation equivariance, and also not just even rotation equivariance that have been done in the literature. We want to do perspective equivariance, which are captured by special linear groups. To do that, there are two main approaches in the literature. One is a regular group CNN, the other one is steerable CNN. The regular group CNN lift the input function onto the group. So now, instead of just a function on the vector space, now the function is on the group. Then we perform convolution and integral on the group. And in practice, we discretize the group and then record the response at each discretized group point. Steerable CNN, on the other hand, still performs convolution on the Rn domain, but the constraint, it'll show in next page. They constrain the kernel in a way that the learn feature can be directly transformed by some representation of the group. Like this. So now let's take a look, first take a look at how we can use regular group convolution to construct a perspective equivariant neural network. Like I said, because we only have finite computational resources, we need to discretize the group and do finite summation over the group. For a rotation group, it's easy to discretize. We just set the amount of degree that we want to discretize, then we sample along those degrees. But how do we discretize for a special linear group? It turns out that there's a thing called Iwasawa decomposition. So for every element in the special linear group, we can decompose them into K, A, and N subgroups, where K is the rotation group that we understand. A is this diagonal matrix. And then N is this upper triangular matrix. So with this decomposition, we can use the parameters from each subgroup to discretize the group. For rotation, we could just use a row P shell. For A, we just use A and B. For N, we use X, Y, Z. So this is one of the results. We trained the neural network on the MNIST classification dataset. And MNIST dataset is a handwritten digit dataset that we want to classify from an image what this digit is. We train the network on original image that is not perturbed by any transformations. Then we test it on affine transformations, which is parallel preserving transformations, and homography transformation, which are line preserving transformations. If we use two layers of convolution, we can see that our equivariant network has a better performance than CNN. However, if we use 6 convolution layers, we can see that the CNN performance start to catch up with the equivariant network, even though equivariant network still has a little bit better performance. If we use the 9 convolution layers, you can see that the CNN performs pretty well, but we are unable to run the equivariant network because of the dimensionality of the system. So that shows one of the drawbacks of regular group convolution, that is, it's memory demanding due to the high dimensionality of the group. For example, let's say if we want to only discretize 5 discretization for each dimension, that would be 5 to the 6. And then if we use image size of 40 and then feature size of 128, one single feature would amount to 12.8 gigabytes. And that's without the weight and batch size and other stuff. So this regular group convolution is infeasible for higher image resolutions due to the memory consumption constraint. That leads us into investigating how to design a steerable CNN so that it's more memory efficient and we can still perform the perspective equivariance network. So steerable CNN, again, we constrain the kernel in this way so that the neural network itself is equivariant. And remember how I talk about how we have an action on the function? So group action on the function, we have a transformation in the domain and another representation on the codomain. If we constrain the kernel like this, the input transformation will get canceled out and then automatically carry to the output. So it will be equivariant. But in order to design a kernel like this, it often requires irreducible representation study or harmonic analysis of the group. And for non-compact groups like special linear group, it's a little bit tricky to deal with. And that's probably one of the reasons why there are not many special linear group equivariant network in the literature. In this work, we use a method proposed by Max L. We parameterize the kernel using the equivariant MLP instead. So we don't explicitly write down the basis for the kernels, but we parameterize it using the equivariant MLP. The idea is that if the kernel is something like this, which is a matrix, if we do a vectorization of the matrix, all the representation on both sides will become the representation only on the left-hand side. Then if we write down this representation, then we can use the equivariant MLP to model this. So we can take a look at one of the results. So the right-hand side is the learn feature, which we set it to be invariant. So it shouldn't change when input is transformed. Then we feed different transformed input into the network, and we want to see if the network can give us stable features. We can also take a look at the equivariant features. So we have this non-transformed image. We pass it through the neural network, and we get the result from different layers, like layer 1, 2, 3, and 4. Then because we are using a steerable approach, we can transform the learn feature. So we transform the learn feature using the transformation. Then we can also transform the input to get another transform input and then feed it into the system. If the network is equivariant, these two should be exactly the same. In the first few layers, you can see qualitatively they look similar. But in the last one, they are not exactly the same. And we are curious about why is that. Our assumption is that because the input image is too small, it's 40 by 40, when we are doing this swapping transformation, there will be some artifacts arises from the bilinear interpolation of the system, of the image. So to test this, we compute equivariance error quantitatively with respect to different image resolutions. So here's the result. We compare it with the CNN, which is not equivariant at all. And you can see that the equivariance error of CNN is pretty high all across different image resolutions. But for steerable CNN, when we have 40 by 40 image size, which was the MNIST data image size, it has a higher equivariance error. But when we increase the resolution to 512, the equivariance error is significantly reduced. We can also see a qualitative result of a high resolution image feature learning. So we feed the network into, feed a transform input into the network and get our feature from the CNN and ours. We can also feed the original image into the network and then transform it afterwards. And you can see that the feature from the CNN is completely different, but it's blocked. But the feature from ours qualitatively looks the same. So a quick summary of this chapter. I talk about two approaches for constructing perspective equivariant learning. And I show that steerable CNN is more memory efficient than regular group CNN, and talk about the drawbacks of regular group CNN. So in conclusion, this thesis, there are 4 main chapters. The first one is a real-time symmetry preserving state estimation library that runs a variety of different robots. The second one is a learning-based full contact estimator for leggy robot state estimation. Third one is a joint equivariant MLP for the algebraic feature learning. Last one, I talk about 2 approaches for constructing SL3 equivariant CNNs. future works. One of the future work that I'm interested in working on is to extend the homography equivariance network to non-planar objects. Like I said earlier, the current network that we develop can only work with planar objects in the world. But to model the non-planar object, we need to deal with the occlusion that arises due to the 3D shape of the object. So I'm interested in looking into how we can use probabilistic framework into a group convolution or geometric deep learning framework. A second part of future work that I'm interested in is how we can apply equivariance in the manipulation and endorsing understanding. For example, models the part equivariance of articulated objects. If we can have some rotation or translation constraint on the oven here, then we can know how they could be moved. I'm also interested in object dynamics prediction, like giving the robot a sense of how object can be moved. Lastly, I'm also interested in deformable object modeling, so like we can actually let the robot fold close or something. And here are a list of publications through the course of my PhD. And these are the open sourced software that I have built. Okay, then comes to the acknowledgement part. I want to thank everybody on my committee. Tumani, thank you for being a good mentor and good friend. Thank you for believing me even when I don't believe in myself. To Jesse, thank you for being such a good role model for me for such a long time, and thank you for all your support ever since I was a master's student. To Ram, thank you for all your feedback on my project and the discussion that you had. Those are really helpful for completing my thesis. For Vasilios, thank you for all your advice that you gave me, and thank you for being on my committee. Those are really helpful for me to figure out if I want to go to academia or industry. I want to thank my collaborators, especially I want to thank Lu, Minghan, and Ray for your mentoring throughout my PhD. I want to thank Tinjun for helping me on so many projects. I want to thank Professor Gu and Zijian for the collaboration on the state estimation project. I want to thank Greg for the Iwasawa decomposition idea and the discussion on the homography transformation matrix equivariance work. I also want to thank Ross for his mentorship during my internship at Amazon. And then I want to thank everybody in the lab for your support throughout all these years and the interesting discussion and interaction we had in the lab. I'm trying not to cry, sorry. I want to thank the people in the community, especially Denise. I think you are the angel to a lot of us in the program, and also Damon. I want to thank all the people who have interacted with me and for creating such a great community for robotics. I also want to thank Taiwanese people who have helped me since day one I arrived to the US. Yeah, thank you for your attention.